Hello everyone, welcome to week 8 of our biochem reviews. I hope that your exam last week went well, and I hope that you're excited for this next unit because it's going to be explaining a lot of kind of the weird and technical aspects of enzymes, and then it's going to go into a lot of glycolysis and metabolism, and that's a really big unit as well. So I'm just going to go ahead and jump right in. Number 1, allosteric regulation involves covalent binding of a regulator to the enzyme in a site other than the substrate binding site. So there's a lot to unpack in this statement to make sure that we know whether it's true or false. So the first important thing is regulator. Okay? A regulator can be either an activator or an inhibitor. Okay? And they do exactly what they sound like they do. This increases the rate of reaction, and this decreases it. And I should say rate of reaction, or it increases the binding affinity by decreasing K. But regardless of which it does, it somehow improves the reaction, or it slows it, or it halts or decreases the rate of reaction in some way. Right? The next is it's to the enzyme, not the substrate. That's a really big point. And finally, this last part, a site other than the substrate binding site. So this is really important because when we talk about inhibition, in the last unit, we talked about competitive inhibitors, non-competitive inhibitors, uncompetitive inhibitors, all that stuff. So both competitive and non-competitive inhibitors are able to bind to the substrate binding site of an enzyme. Allosteric regulation is nothing like inhibition as we've talked about because it's not about the substrate binding site and it's not about the enzyme substrate complex. It's kind of very different. And there's actually one other really important thing to note here. The type of binding. It is not covalent bonding. Okay, it's a non-covalent bond. Something like a hydrogen bond, something like a dipole, kind of the affinity between the two, things like that. It is not a covalent bond. That makes the number 1 false. Okay. Now there are a few other types of regulation, such as phosphorylation. So phosphorylation is something that we discussed in the last unit a little bit, but we're going to talk about it a little bit more here. So phosphorylation, typically done by a kinase. So a kinase adds a P to whatever you're dealing with, and then if you want to remove it, you use a phosphorylase. Okay? So what adding phosphorus does is somewhat enzyme dependent. So in some cases, adding a phosphate group will inhibit or deactivate the enzyme. In some cases, adding a phosphate group will activate the enzyme. It'll speed it up. It'll speed up that rate of reaction. So let's talk about the amino acids that we could be dealing with phosphorylation. So one thing that I like to do is I like to kind of draw the structure that I'm dealing with. So I know that phosphorus is PO4. Phosphate is PO4. And there are some double bonds, there are some negative charges, but the real important thing that I want to highlight is we're dealing with oxygens, okay? And that's kind of the giveaway for how we can figure out which amino acid side chain could be phosphorylated. Serine is CH2OH, that's the side chain. Aspartate is, I believe, 2 carbons and then carboxylic acid. Glutamine is, 3 carbons, 1, 2, 3, and then an amide, H2, and then tyrosine is the ring, and then an OH. Okay? So when we look at these, serine has an OH group, aspartate has an OH group, and tyrosine has an OH group, meaning, that the only amino acid side chain that doesn't is glutamine, and that's actually the answer. Glutamine cannot be phosphorylated. Okay? The next question asks, what is pro-insulin? So pro-insulin is a very common example that's used both to teach this concept and on exams to make sure that you understand this concept. So Pro-insulin looks like, and I'm going to try to use different colors here so that I can kind of show what I want to show a bit better. Like that. Almost like a paperclip. And then between a couple of these spots, there's disulfide bridges. So pro-insulin is converted to insulin, by cleaving at two of the sites of the peptide, two of the peptide binding. It basically cleaves that blue part. And when it cleaves that blue part, the rest of insulin really is held together by these disulfide bridges. So when we talk about pro-insulin is what's called a zymogen, or a precursor. I might have spelled that wrong. And it's not insulin without sulfide bonds. It's not the active form of insulin. It's actually the exact opposite. Pro-insulin is the inactive form of insulin. Inactive form of insulin. Okay. It's not insulin without a connecting chain, it's insulin with a connecting chain. This blue part is that connecting peptide chain. Connecting, also called a connecting peptide. Excuse me. So the really important thing to take away from pro-insulin is this is yet another way that we can regulate enzyme activity. There's allosteric. There's things like phosphorylation or some form of post-translational modification like we talked about with like acetylation and phosphorylation. And the other ones that I don't believe you guys had to memorize. There's creating a precursor and then having this cleavage process occur only when insulin is needed. Things like that are different ways that we can regulate our enzyme activity. Okay, so the next question is, and you want a little bit more space, here we go. A, and A is just some protein, reacts to form B in a reaction catalyzed by the enzyme E1. B then reacts to form C in a reaction catalyzed by E2. C, the final product in this pathway, binds to E1 and speeds up the rate of B formation. What type of allosteric effector is C? So this is kind of a lot of words. And when I get these kinds of word problems, I don't like to just try to figure it out from this. I like to draw almost the reaction pathway or the map of that reaction. So it tells me A, oh, actually, let me switch to the black. There we go. It tells me A reacts to form B, and that reaction is catalyzed by E1. So I'm going to put E1 above this arrow. Okay. B then reacts to form C. Okay, so that's this part. A reaction catalyzed by E2. Awesome. Okay, so that's what we're actually dealing with here. First two sentences, reaction pathway, done. Okay. C, the final product in this pathway, binds to E1. So I'm almost going to think of it like C goes back this way and binds here. And when it does, it speeds up the rate of B formation. Okay. So what type of effector is C? So the fact that it's speeding up B formation, speeding something up tells me it's not going to be an inhibitor. So all these words or all these choices that have inhibition in them are wrong. Okay. So C is an interesting point. Regulatory enzyme. So a regulatory enzyme is an enzyme that affects other enzymes or an enzyme that affects reaction rates. But C is not an enzyme. C is just the product. And so C, I should say, product C is just the product. Therefore, answer choice C is incorrect. I apologize for that confusion. This is an allosteric activator. Okay. Now I'd like to talk about a couple of these points, A and B, very briefly, since I skipped over them, just to make sure we all know what they are. So an allosteric inhibitor would be if product C were to bind to E1 and slow down the reaction. That would make it an allosteric inhibitor. And it would also be an example of feedback inhibition. So the idea of feedback inhibition is the idea that I want to activate my my first enzyme, so that my second enzyme and my third enzyme, my fourth, and however many, all do their job and produce my final product that I need. But once I have that final product, I can stop. I don't need to keep going. I don't need to rush through anything. I want to stop making that final product because I don't want to waste my materials. So final product C or D or F or Z even will go back and bind to E1 and it'll inhibit E1 or E2. And that is called feedback inhibition because it forms what's called a feedback loop, okay? Where the final product inhibits the first reaction, and as final product concentration goes down, E1 is then free to act on A and keep forming and start forming more product only when we run low, okay? So, shifting gears a little bit, we've been talking a lot about general regulation. There's this concept called cooperativity, and cooperativity is the idea that if an enzyme binds to maybe 2 different things at once, or 3 or 4, that binding to the first can affect binding to the other however many, okay? When that happens, it can either increase or decrease that, it can either increase or decrease that the rate of binding and thus the rate of reaction with the rest of it. So needless to say, if you've got cooperativity and if you've got something that's not, or something that is being affected and being changed, your reaction rate isn't just going to follow Michaelis-Menten kinetics. Okay, so we all remember this curve that describes the reaction rate. How very briefly with kinetics, first order at first, 0th order when saturated. That idea, that doesn't exactly work with cooperativity. Cooperativity forms what's called a sigmoidal curve, and I think of it like an S, and then it kind of trails off. So it starts off very, very slow. When substrate concentration is low, reaction rate is going to be very, very, very low. Then, at some point, it starts going up. And that point is when your substrate concentration, when substrate A binds, and that affects the enzyme in order to allow substrates B and C, if they're the same or not, to also bind. And we're going to talk about a couple examples, and we're going to talk about a couple models that help us explain this. But that's the basic idea. And the important thing is with cooperativity, we see a sigmoidal curve. Okay. A question that commonly comes up is, how do we figure out cooperativity? Is something more cooperative than another? The answer is yes, but for the purposes of this class, it's not something that's covered too deeply. There's something called the Hill coefficient, and this Hill coefficient is a measure of cooperativity, whether positive or negative, but it is beyond the scope of Biochem 1. Number 6, in the MWC model of allosteric regulation, which of the forms of the enzyme is able to bind to a substrate? So let's talk about the MWC model. I'm going to be honest, I don't know what it stands for. It's the 3 people who came up with it, but we don't need to know what it stands for because it doesn't give anything away. It just tells us which model we're talking about. So the MWC model allosteric regulation says basically, I want to use different colors for this, that this enzyme has 2 forms, a tense form and a relaxed form. And see if I can draw this well. I think that's okay. And we'll call the red one the relaxed form, R0, and the blue one the tense form, T0. So my substrate, and this is going to be an enzyme that has 2 of the same substrate. So rather than binding to A and binding to B, it's going to bind to 2A. That substrate looks like a slice of pizza. Okay? So based on that, and let me label this substrate. Oops, there we go, substrate. Based on that, it's going to want to bind to the relaxed form. Okay, and these two are in equilibrium with each other. And their equilibrium constant is called L. It's not something that's really talked about. I've seen some professors ask questions about it on exams. I've seen some professors barely talk about it. So it's a very professor-dependent thing how much you'll need to know for. So like we said, it's pretty obvious that the substrate is going to bind to the relaxed. So that's the answer to this question. But the important thing with the MWC model is, and I think you guys can see number 7 at the bottom, why is the KNF model called the sequential model? This is the sequential model. The MWC model is not sequential, okay? Excuse me. Actually, I'm getting a little bit ahead of myself. Let me keep talking about the actual model before I get into the names. So one really important point about the MWC model is that since these two forms are in equilibrium, when R0 binds to something, it affects that concentration, because now one R0 molecule is being removed since it's bound to something, and another R0 model, and so that shifts equilibrium because R0 is decreasing. It shifts the equilibrium, in this case, to the left to form more R0. Okay, and we're going to talk about equilibrium with respect to that in a bit. But so I had kind of alluded to this, and then I realized I was getting ahead of myself. I said in number 7, the KNF model is called a sequential model. The MWC model is called a concerted model. Okay, and the reason for this, and I think it'll be clearer once we talk about the KNF model, but the reason for this is you've got two different forms. You're either relaxed or you're tensed. There's no middle ground. And so because of that, it's either all going to bind or none of it's going to bind. Okay? So let's talk about it with respect to number 7 and the sequential, the idea that this KNF model is sequential. So the KNF model basically says, and this one is a little bit hard to draw, but and we're going to kind of use similar notation. The blue is going to be, it's not tense, they don't call it that, but the blue is going to be the not binding one, the one that doesn't like to bind as much. Okay. So what happens is, as soon as my first substrate binds to the first, I'm trying to keep this all color-coded, to the first subunit, I get a conformational change. In this case, I get a conformational change in the red one. Okay? I'm sorry, in the top right corner. And that's because it's bound to a substrate, so plus S. The binding of the first subunit to a substrate causes a conformational change in the next subunit. So rather than getting one bound circle and 3 squares that don't want to bind, we're going to get one bound circle with an S and one unbound circle that wants to bind. Okay? So like we said, the binding of the first subunit to its substrate changes the conformation of that substrate, and it changes the conformation of another, I'm sorry, not of the substrate, it changes the conformation of the subunit and of the next subunit. And so that subunit will either want to bind more or less. And then when this one binds to a substrate, we're going to see another conformational change. And so on and so forth. And so as each substrate, as each subunit binds to a substrate, a conformational change is induced in the next subunit as well as the current one. So, and I want to kind of emphasize this because it can be a little bit weird. When this subunit, the top right subunit, binds to a substrate, it changes form. So the first thing to keep in mind is the first subunit, when it binds, changes its conformation. That then affects the next subunit over. So that forces the top left one now to change as well, and that lets it bind to S, to its substrate more or less. Okay? I'm just going to pause here to take a moment to drink some water, but I want to make sure that this makes sense. So I want to pause and let you guys digest as well. Okay. So number 8, how does an activator increase substrate binding in the MWC model? Okay. So coming back to the MWC model, it's this thing up here, the idea that we have a relaxed form and a tense form. But if we bind to an activator, well, the activator, it changes something, but I don't know what it changes. So here's the deal. So, and I'm going to kind of work in this empty space right here, and I'll see if I can make sure that it's appropriate. So we're going to call this R0, just for the sake of not having to draw a million of these. And then the tense form, I don't want to make red because I've been using blue. So we'll keep the tense form as blue. So now your relaxed form can bind to an activator, which we're going to call A. Okay. And I'm just going to say that's the activator. Your relaxed form can also bind to a substrate called S. And I guess I'll draw that in a circle. So this will be S. Okay. Or it can bind to both, but I'm not going to finish that triangle. So when it does bind to either of these, it becomes what's called R1S or R1A. The S and the A being the substrate and the activator respectively, and the R1 being one thing has bound rather than 0, which is what R0 is. Okay, so let's talk about this with respect to Le Chatelier's principle. Thinking back to Gen Chem 2. When I bind to an activator, so we're looking right here, that increases this concentration and decreases the concentration of R0. Okay, in other words, my activator, by decreasing the concentration of R0, is shifting the R0 to T0 equilibrium to the left and causing the formation of more relaxed form, causing the formation of more of the relaxed form of the enzyme, which can then bind to my substrate. Okay, so that's how an activator can be obtained using the MWC model. Okay, now what about an inhibitor? And for the inhibitor, I'm going to use red, just because I'll keep using blue, and then I'll switch to red in a little bit. So whereas an activator will bind to the relaxed form, an inhibitor will bind to the tense form. Okay, so plus I, and I'll draw this again with a triangle because I'm running out of shapes. This is our inhibitor. Okay, the same explanation that we just had with our activator is going to apply here. As an inhibitor binds, it decreases this concentration of the tense form, and that shifts the equilibrium to the right, forming more of the tense form and decreasing the concentration of the relaxed form. So, since there's less relaxed form, there's less substrate binding. Okay? So, in my opinion, the MWC model is really weird to get a hang of, but once you've got it, it's a lot more intuitive. Okay? And I'm going to go ahead and skip ahead just a moment so that we can actually see a picture of this that's better drawn. So here's a great picture that's in your slides and in your book that really helps to show this. So the things that I want to highlight are exactly like we talked about. Your activator in this case is a triangle. Activator. When it binds to R0, you get R1A, like we talked about. That, remember, decreases this concentration, so this shifts over. But also, this does a better job of showing kind of how everything can bind. So R0 can bind to your substrate, or it can bind to your activator. And then once it's bound to one, it can also bind to the other. And so because of that, we get this, don't want to skip ahead, we get this, this idea of R1 being multiple different things. And as these all bind, we're actually, as these all bind, we're actually going to increase, or I should say, we're going to keep shifting the equilibrium toward R0 to make up for the binding, changing it, okay? Likewise, on the other side with our inhibitor, your inhibitor binds to the tense form. And the thing I want to point out with the tense form and the relaxed form, and this is obviously just a drawing, but the shape of each binding site, just keeping it general, is different in the tense and relaxed forms, allowing for different things to bind. So it's not that the activator chooses to bind to the relaxed form and the inhibitor chooses to bind to the tense form. It's that they're forced to bind there because that's the spot that they have. Okay? I want to make sure that makes sense. I'm going to say it again. The activator only has a binding site with the relaxed form. The inhibitor only has a binding site with the tense form. Okay? All right, and that's numbers 8 and 9. So number 10, in the KNF model, how can we differentiate positive and negative cooperativity? So when I described this KNF model, I said it induces a conformational change. I kind of hinted at with when I drew this. Let me see if I can have I'll use a blue highlighter just to show them apart. This plus S bit, this substrate can now bind to this green top left subunit. We don't know whether that binding is increased or decreased, okay? And I'm going to go ahead and just show the diagram from your slides in your book because I don't know that I could draw this well. But I'd like to talk about it a bit because I think it's really confusing. So, like we said, the first step is the binding of the first subunit to its substrate, which induces a conformational change in the bound subunit. So, S binds to this subunit and changes this let's redraw that, and changes this subunit into the circle, okay? Now, that subunit being bound somehow affects the subunit next to it, and we're going to have an example later on where we can kind of talk about how it does affect that more specifically, but for now, just it changes things. In this case, the change is a little bit easy to tell because your square is kind of rotating into a diamond. So this could be something as simple as the substrate binding forced the two subunits to move relative to each other, okay? And that's one of the biggest ways that these conformational changes happen. It's not always a huge shift in the structure. It could be as simple as moving by a couple degrees, a couple angstroms, things like that, okay? So now, this conformational change affects the substrate binding of the second subunit somehow, okay? So what these next bit is telling us, if the relative affinities of the various conformations are those, and this is kind of confusing, but for now, let's ignore S. Okay, we're just looking at this part. If the diamond binds better to S than the square, positive homotropic effects ensue. In other words, if this conformational change to the diamond is better for substrate binding, that's positive cooperativity. Okay. On the other hand, same exact thing with this one, except we're still going to look at this one, and the difference is that the diamond and square switched places. So if the original form is better at binding to our substrate than the new changed one, then it's negative cooperativity. Okay. So I'm going to take a moment to talk about this one more time because it is, in my opinion, one of the more confusing parts of this section. I didn't really understand this well when I was taking the class. So the binding of S in the KNF model to the first subunit induces change in that subunit. The change in that subunit then changes. It transmits, as the book calls it, a conformational change in another subunit. And this doesn't just have to be 2, it can be 2, it can be 3, 4, 5, however many. But when the second subunit changes, the unbound subunit, we have to ask ourselves, which form is better for binding? The original form or this new changed form? And if the original form is better, we have negative cooperativity because we decreased our binding. And if we changed that second subunit into a better form, then we have positive cooperativity because the binding is increasing. Okay? All right. So that is the basics of the two models. Now we're going to have an example, okay? And that example isn't enzyme binding to substrates in a traditional sense. It's hemoglobin binding to oxygen. So whereas an enzyme would be used to catalyze a reaction, hemoglobin isn't reacting with oxygen, isn't changing oxygen in any way. It's transporting it, which makes this a little bit different. It still follows the exact same principles of these models. It still talks about these various things. So we're going to go ahead and get into it. So in the following figure, which protein shows sigmoidal oxygen binding kinetics? So this is more a review, and also because I didn't know that I could draw a perfect sigmoidal shape. So if we can see here, I lost my mouse. There it is. Hemoglobin has this slow slope, and then it jumps up. It jumps up, and then, like the other one, it levels off. Okay, that is classic sigmoidal bonding, or I should say sigmoidal kinetics, or a sigmoidal curve. Okay. On the other hand, myoglobin, let's see, first order at the beginning, 0th order at saturation. At saturation, despite not being enzymes speeding up reactions, hemoglobin and myoglobin follow the very similar kinetics. Okay. And just for the record, because I know sometimes it can be confusing, this these dotted vertical lines of working muscle, red muscle, venous, and arterial PO2 are basically kind of telling us the working muscle. They're telling us the affinity of. They're telling us the concentrations. So partial pressure of oxygen, the pressure of the concentration, in the arteries is close to 100%. In the veins, it's close to 30%, and so on. So let's kind of talk about how that affects things. So we know that blood is going to travel in our arteries to our muscle, and then empty hemoglobin, unbound hemoglobin, that doesn't have oxygen, is going to travel back to our lungs to get more oxygen. So arterial PO2 is very, very, very high, meaning that both hemoglobin and myoglobin in the arteries are going to be really, really saturated. Okay. Then in the veins, not so much. Okay, 30% means hemoglobin's only going to be down to like 70% oxygen, if that. Myoglobin is still going to be quite high. Okay? But let's talk about the working muscle, because this is kind of something that I think is really great to emphasize. In the working muscle, hemoglobin has 10%, somewhere around 10% saturation. In other words, if I have blood traveling in my artery until it hits my muscle, well, as soon as hemoglobin gets near my muscle, it wants to drop its oxygen. It has a terrible binding affinity for it because the partial pressure of oxygen is so low, and that's why hemoglobin releases oxygen there. Okay, it all comes down to binding kinetics. Okay. So we answered that question. Let's go to number 12. How does hemoglobin show both the MWC and the KNF models? Okay, so this is going to be a very strange explanation, I think. So hemoglobin in general has 2 alpha subunits and 2 beta subunits. Okay, the specifics behind them don't matter too much for now. I really don't think they'd matter much for the purposes of this class, beyond what we're going to cover today. So I wouldn't worry about how they're different. Just know that they're different. Okay, and I'm going to draw the. Let's use green. Blue. I apologize. The beta is going to be gray, and the alpha is going to be blue. And beta. Okay. So, just like we talked about, or I should say, just like we talked about with the KNF model, first thing that's going to happen is one of our subunits is going to bind to an oxygen. Okay, and in this case, it's going to be in one of our alpha subunits. Okay. Okay. Sorry, I apologize. I was trying to figure out the best way to draw this. Beta, beta. Okay. And this alpha subunit, that induces this conformational change. And the fact that I'm coloring it in tells me that it's bound to something. Okay. That conformational change in the first alpha subunit, and this is kind of hard to explain, so I apologize, it's going to be a little bit unintuitive at first. The binding, or I should say, the structure of hemoglobin, I could have drawn this earlier, I apologize. So the structure of hemoglobin is there's an iron center, and then basically 4 nitrogens all around. And these nitrogens do a really great job at what's called coordinating this iron. So it's called a porphyrin ring, by the way, the structure. Excuse me. And there's a lot more behind this, but for now we really only care about the nitrogens. Excuse me. In this state, iron is kind of, if we look at it in 3D, it's almost popping out of the ring. So if the ring is flat right here, iron is just sticking up a little bit in the center. The binding of the first subunit to oxygen allows that iron to flatten out and move back into the plane of the porphyrin ring. Okay? That causes a transformation in the next alpha subunit. Okay? And that transformation in that next alpha subunit increases bonding affinity. So this one is still shaded in because it's still bound to an oxygen. This one is not. But going back to that idea that we talked about just right here, in this case, the circle form of our alpha subunit is better than the square form, which means that the circle form is increasing binding, and in fact, that's exactly what we see. I apologize, it'll take me one moment to draw this. Okay, and I did kind of give it away, but just in case, I'll say it real quick. This first part is literally exactly what we just talked about with respect to the KNF model. Okay. KNF. Okay. But now there's a difference, because rather than the binding of the second subunit to an oxygen affecting the beta subunits, that's not quite what happens. What's going to happen next is, and this is kind of weird to think about, but when you have your two alpha subunits bound, then there's a large conformational change, not just a small one, and I believe it increases the angle, like before it's kind of a straight line, beta, beta, alpha, alpha, then it kind of forces a rotation. So it's beta 1, beta 2, alpha 2, beta 1, and it's kind of crooked. I know that it doesn't make a ton of sense. Your notes kind of have a good description of it, and your slides do, but unfortunately, I'm not good enough at drawing to do that. Okay. And that conformational change, though, affects the beta subunits. It increases the binding affinity of the beta subunits. And just for the sake of time, I'm going to go ahead and only fill in one more reaction, although you can have all 4 bound to all 4 subunits bound to oxygen, excuse me. But for now, I'm going to leave it empty. And we're going to, so now, coming back to this kind of idea of that conformational change, I drew a double arrow here. And the reason that I drew a double arrow here is because this is basically the KNF model, or I'm sorry, the MWC model. If we think of this as the tense form and this is the relaxed, what we're seeing is now as soon as hemoglobin has oxygens bound to both of its alpha subunits, that can induce a conformational change that makes it able to bind more with its other subunits exactly like we see here. So the first half of hemoglobin binding is absolutely the KNF model. The second half is the MWC. Now you might be asking yourself, or you might be asking me, is every enzyme both? Is every enzyme one or the other? I thought they were both saying the same things. Going back to, I think it was question, no, it wasn't question 9, it was question 5. Let's see. No, question 7. The KNF model is called the sequential model, and the MWC model is called the concerted model. Okay? This is the big difference between them. Okay? In KNF, it's one, then another, then another, then another. In MWC, it's all at once. Okay? Some enzymes show similarities to the KNF model. Some enzymes show similarities to the MWC model, and some proteins, like hemoglobin, show both. Okay? That's the big difference between the two models, kind of in a really good example that shows them both well. So I want to just very briefly go over it one more time to make sure we're okay with it, and then we can go ahead and move on. So at first, you have your hemoglobin, everything is unbound. As soon as you bind to your first oxygen, which shaded in, binds to a subunit. That subunit changes its conformation. The change in the conformation of the first subunit changes the conformation of the second alpha subunit, which allows it to bind a lot more easily. Once both alpha subunits have bound, this resembles a tense form because your beta subunits are in their less favorable conformations for binding. When the two, then that equilibrium shifts and allows the two to bind more easily, and that resembles that MWC part. Okay? A really important thing to note here is, once again, I'm going to remind us of why. This changes because the iron is able to shift into the plane of the porphyrin ring. Porphyrin ring. Okay, I apologize, I ran out of space and kind of wrote it all over. Okay, this shift is because the alpha and beta subunits rotate about 15 degrees, and that rotation, that conformational change as we've been calling it, that the way that I think of it is it almost opens up the substrate binding sites, but really it's more that it makes it more favorable to bind in some way. Okay, but yeah, so that's the model. So number 13 is kind of a little bit more on hemoglobin. So the question is, why does fetal hemoglobin have a higher affinity for oxygen? So fetal hemoglobin is the hemoglobin that a child or fetus has while they're in the womb. So one of the really important things with it is it has to have a higher affinity for oxygen, because in order for the mother or the person carrying the child to give them oxygen, is that oxygen has to be able to dissociate from the hemoglobin of the mother into the child's bloodstream. So because of that, it has to have a higher affinity for oxygen. Why? There are actually two reasons, and there are answers here. The first is B. So fetal hemoglobin is alpha 2, gamma 2. Okay, it does not have beta subunits, it has gamma subunits. Okay, now those gamma subunits have a lower affinity for BPG, and BPG is 2,3-bisphosphoglycerate. So bisphosphoglycerate is a negative allosteric effector of HB. In other words, it's an allosteric inhibitor. Okay, and so when it's present, it binds to hemoglobin and it affects how much oxygen it's able to actually pick up. Okay. Now there's one thing that I want to kind of draw our attention to. Structure dictates function. That's something that we learn a lot in biology classes. But here specifically, there's a structural component and there's a functional component. In other words, we can draw a conclusion from this question, and this is actually true, that 2,3 BPG affects the beta subunit. Okay? That's kind of something that I want to try pointing to. Okay? So the difference between a K system and a V system. So in the very first question, I kind of tried to watch my words a little bit when I said it doesn't necessarily affect the rate, but it somehow improves things. And I think I did slip up once or twice and say it increases the rate. It's not always the case. And that's kind of the idea of the K and V systems. So a V system, and actually I picked the K system first for some reason. Let's do the V system first. The V system is exactly what it sounds like. This is with no allosteric inhibitors, so I'm just going to say no allosteric. When you have an activator increases V, and when you have an inhibitor, or I, inhibitor, it decreases V, okay? A K system is the exact opposite. Rather than affecting V, it affects K, right? It's a K system. So in a K system, your inhibitor increases K. Inhibitor increases K, remembering the idea that K is inversely proportional or inversely related to that binding affinity of the substrate for the enzyme. So increasing K decreases affinity. Affinity. Okay. A on the other hand, A decreases K and increases affinity. Okay? So that's the difference between a K system and a V system. And it's really important to know this difference because your enzyme isn't just speeding up a reaction. It is speeding up a reaction, but the question is, how is it speeding up that reaction? Is it removing the saturation, or I should say, is it increasing the saturation threshold so that V can increase? Or is it increasing the affinity of the substrate for the enzyme, or the enzyme for the substrate, so that more can be bound, so that when that reaction happens at its speed, more of it can happen because more is being bound? These are more about just how enzymes work, okay? Next question, myoglobin. We talked about myoglobin for about 30 seconds right here when we said it kind of looks like a Michaelis-Menten graph and then moved on from. Why doesn't it show that allosteric that hemoglobin does? Because myoglobin also has a porphyrin ring. Myoglobin also has an iron. It also binds oxygen. What's different? Well, hang on, I just spoiled it. It does bind to oxygen and it does contain iron. So all that's left is it a monomer or is it an oligomer? So with most of what we've been talking about so far, the KNF model relies on it being an oligomer. The MWC is a little bit less specific about that. It can be a monomer, but we can also see it in oligomers. But importantly, the first step in hemoglobin allostery and cooperativity is the KNF model. So the reason that myoglobin couldn't have allostery is because it's monomeric. Okay. So the next few questions, I kind of jumped ahead a little bit. So this is all we've done so far is on the enzyme regulation chapter that you've been covering yesterday and tomorrow. This next part is going to be into the introduction of metabolism very, very, very briefly, and that's next Tuesday's topic. I just really briefly wanted to explain some of these terms because I think that be a little bit annoying. Okay, so let's get into it. So the first thing that we talk about with metabolism is why we need metabolism. So very briefly, we need to eat things so that we have energy and nutrients. We use that energy to power our body, and we use those nutrients to build things up. So there's the basic spiel about metabolism as basic and straightforward as I could get it. And as you see in number 17, it's made up of catabolism and anabolism. We'll talk about those more specifically in a bit. But we as humans eat foods to get our energy. Plants use light. Trying to think, I'm sure there are other things that species use, but I can't think of them off the top of my head, so don't worry about them too much. But the point of it is there are different light sources. Each different light source, or I should say each species that uses that light source, or I should say energy source, not light source for energy. Each species that uses that source for energy is given a different name. So a phototroph, almost exactly, or troph, I don't know exactly how it's pronounced, exactly like it sounds, uses light for energy. Okay? Now there's a few others. So the first is chemotrophs. And inside of those, there's chemoorgano and chemolitho. Okay? I think you guys can probably guess by the fact that there are 4 choices and 2 of them are very, very similar, that these 2, let me fix that, I apologize. These 2 somehow correspond to these 2. Not too hard to guess. More specifically, exactly like you might guess, organo, organic, and the litho is inorganic, which just leaves CO2 for the autotrophs. Okay? And an important thing to note is CO2 is not an inorganic or an organic compound. It's kind of left separate. Okay? There's another type that we don't talk about much, and it's called a heterotroph. And a heterotroph, I'm going to write this over to the side. It uses organic compounds not for energy directly, but as a carbon source. Carbon source. So the reason that this is very, very separate is when we think of autotrophs, autotrophs use CO2 for energy. Well, CO2 is that carbon source almost. So heterotrophs are kind of a mix between chemoorganotrophs and autotrophs because they're using organic compounds to get carbon and then they're using that carbon for energy. So hetero because they're in between 2 things. Okay? All right. Next is that idea of metabolism and catabolism. So I talk about them as breaking down and building up, but we can also think of them in terms of oxidation and reduction. Okay? So the general gist is one of the biggest compounds within metabolism is NADP and NADPH. Okay? And one of catabolism or anabolism forms them, and the other uses them. So NADPH is what's called reducing power. It provides a lot of the power for biosynthetic reactions. It gives us the power that we need to build stuff up. So one of our anabolism, catabolism, one half of metabolism is basically built around oxidizing NADP plus to NADPH, and the other one is built around using it to build stuff up and then kicking out NADP plus as a waste product. So NADP plus, or I should say, so catabolism is the food we eat, in simple terms. It's breaking down nutrients into simpler, smaller products. So it's breaking stuff down. I lost my mouse, there it is. Breaking stuff down, okay? And that breaking stuff down is there to form NADPH. So this is the catabolism arrow, catabolism. And the anabolism arrow is on the other side. So let's talk about oxidation and reduction. Who remembers those? So oxidation, if we remember, is the increase in oxidation state, or it's the increase in charge, as I sometimes think about it. Anabolism is the opposite. So I'm sorry, not anabolism. Reduction is the opposite. So because NADP plus has a higher oxidation state than NADPH, the reaction to form NADPH is reductive. Okay? Say that one more time. Because I apologize. I have it backwards. So yes, this reaction is reductive, but remember that they're never done on their own. We call redox reactions because they're together. So if NADP plus is reducing, that means that catabolism involves oxidation. Okay, I apologize for that confusion. It's A. I'm going to go ahead and repeat it just to make sure. Because NADP plus is in a higher oxidation state than NADPH, it needs to be reduced. Okay? It is reduced in the process of catabolism. And if catabolism is reducing NADPH, the reactants or the starting materials that we're using for catabolism have to be oxidized. Okay? It's one and the other. And likewise, anabolism, NADPH is oxidized back to NADP+, and in doing so, it reduces our anabolism reactions. Okay? And I have a really great diagram right here that I think shows it better than I explained it. So let me, and this is one that's from your textbook, but I like it a lot. So you start with a reduced fuel here, and then in order for that reduced fuel to be dealt with, we undergo catabolism. Catabolism forms our NADPH, and in doing so, it reduces NADPH, in order to oxidize our fuel into the product. Likewise, as we're building stuff up, biosynthetic reactions are building things up, we oxidize our NADPH. I cannot find my mouse. There it is. Oxidize this, which reduces our product. Now, why is reduction? I called NADPH reducing power. What does that mean? Okay, why is reduction power? So it comes down to the idea that reduction is giving up electrons. Okay, so when I reduce something, I release electrons. That electron flow, and this is something you might have covered if you took Bio 1. If you didn't, basically what that reduction does is it releases an electron and a proton. These two together, or I should say it's mostly the proton, but they help us power what's called a proton motive force. Okay, and it's using the concentration gradient that's going to be formed with a ton of H plus being released in order to form NADP plus on one side of a membrane, and then the other side having nothing. Some cell surface membranes can help transfer this H plus down its gradient, and in going down its gradient, they're using energy, or they're producing energy. Okay, it's exactly like a waterfall. When you use that water to power something, the Niagara Falls, Hoover Dam, things like that. This is the exact same principle, except with protons instead of water. Okay, so the goal of catabolism, coming back here, is to break down our food, in the case of humans, or whatever energy source we're using, into stuff like water, CO2, into waste, in order to form the big two, and I say the big one is NADPH, but ATP is also fairly important, as I'm sure you all know. Okay? Anabolism, on the other hand, is to use the NADPH, ATP, to build biosynthetic products. So these biosynthetic products could include things like building our muscles, which is why, after you work out or something, you want to eat because you're strengthening your muscles. They need to be built up by something like that. Okay. And actually, the final question that I came up with for today, just because I didn't want to keep you guys too long working ahead, is why are our metabolic pathways regulated? Okay. So I want to talk about catabolism and anabolism with respect to kind of the rest of this course. So the next things you guys are going to be covering are glycolysis and gluconeogenesis. Glycolysis is the use of glucose for energy, and gluconeogenesis is the reformation of glucose. Okay. Next thing you're going to talk about after that is glycogenesis, or the formation of glycogen when we don't need energy from glucose just for storage, and then glycogenolysis, which is the breakdown of glycogen. You're going to talk about a couple of other things later on, but with these four, glycolysis, and gluconeogenesis, with glycogenesis and glycogenolysis, your body is very, 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 very efficient. And what I mean by that is, for example, glycolysis. Glycolysis is 10 reactions. 10 reactions. I believe that 7, and I might have that number 1 or 2 wrong, but 7 of glycolysis reactions are using the same enzymes as gluconeogenesis. In other words, my glycolysis, so A, B, C, and so on, this side could be glycolysis. This side could be gluconeogenesis. And it's one word, but I ran out of space. And both of these reactions could be catalyzed by E1, both of these could be catalyzed by E2. You can get some difference maybe here. You'll form D, but in order to form C again for gluconeogenesis, you might need to go into another product and then back into C. But generally speaking, these two reactions are very, very close to opposites of each other. I shouldn't say reactions, these two pathways, okay? And the reason that we have to regulate this so carefully is, for example, if I want glycolysis to happen, well, I need to be very, very mindful to not allow, actually, I think a more appropriate way to do this would be so the point of glycolysis is to get to, let's say, F. So F is the final product of glycolysis. So that's great. So when I want glycolysis to happen, I want to go from A to F. The way that I can make sure that that happens is by, we'll call this enzyme E because it's very specific, is by making sure to inhibit enzyme E. So when I want glycolysis to happen, I have to inhibit enzyme E, because by inhibiting enzyme E, C can go to D, D can go straight to F. If I don't inhibit enzyme E, D can go back to E, E can go to C, and then we can go backwards instead. And so we have to be very, very mindful, because for the most part, a lot of catabolic pathways use very similar enzymes to anabolic pathways. And so because of that overlap, the few reactions that aren't exactly identical need to be very heavily regulated, okay? And it's a very similar story with glycogenesis and gluconeogenesis, glycogenesis and glycogenolysis, but I don't want to go too deep into that because that's a little bit later down the line. I believe it's actually on exam 4, so I don't want to waste your time on it when exam 3 is more pressing. So I'm just going to do a quick recap, and that's it for today. So very briefly, we talked about all of the enzyme regulation chapter, including allosteric regulation, post-translational modification, creation of a zymogen or precursor enzyme, feedback, inhibition, and allosteric inhibition and activation. We talked about cooperativity, specifically the MWC and KNF models of cooperativity, how inhibitors and activators are drawn. Actually, it just occurred to me, I talked about positive cooperativity here with KNF. I never talked about cooperativity with MWC because it's a bit confusing. So let's very briefly talk about that. So when a substrate binds to R, what happens is it forms R1. Okay, great. And for now, I only want to be focusing, by the way, on just this kind of green part. We don't need to focus on the activator parts for now, but just in brief. So when I do that, once again, my concentration of R0 decreases. Le Chatelier's principle is going to cause a shift to the left. So that's how, under MWC, you can show positive cooperativity. Negative isn't easy to show at all, and that's kind of why people realized the MWC model can't describe everything. Okay, and that's what pushed for the idea of the KNF model. Okay, so we talked about cooperativity. We talked about hemoglobin and myoglobin, which I just want to say for the record, I'm expecting to see a lot of on your exam. They're very common questions. We talked about K systems and V systems with respect to how activators and inhibitors really affect the overall rate of reaction and how much of our product is formed. Then we talked a bit more specifically about metabolism and anabolism within it, and kind of the point of everything and the point of regulation. Okay. If you have any questions, please feel free to come into our drop-in tutoring. We're open, Monday through Thursday until 8 p.m. Central Time, and then Friday until 5 p.m. and Saturday until, I believe, 5 p.m. as well. Okay. Thank you all so much for coming, and good luck on this unit.